There is one other thing. I'm including it here as an epilogue because the series is over. Its message has been sent. But this other thing does tie into existential risks in some pretty interesting ways, so I wanted to include it. I'll just leave it here, and you can decide how you feel about it. Back in 2003, Nick Bostrom expanded on a concept that had been around at least since the classical Greeks first recorded their thoughts on it. The idea that what we experience as reality isn't real. The followers of Plato discussed it in the Academy at Athens, and then in the 1600s it was taken up and examined by René Descartes, the Enlightenment philosopher who famously identified that he was because he thought. Descartes wondered if perhaps we exist in a reality that's actually a dream. After considering his own experience with dreams, Descartes decided that if we do exist in a dream, we would never be able to tell. What he experienced in dreams seemed like reality to him, just as much as reality did in waking life. Without any indication to distinguish between the two, we would never really be able to tell the difference. It wasn't until 2003, however, when Nick Bostrom wrote his paper entitled, "Are You Living in a Computer Simulation?" that anyone went to the trouble of formalizing the idea that what we consider reality isn't actually basement reality. Bostrom hit upon a way to examine the nature of reality, and it's based on whether we expect to make it through the Great Filter. He called it the simulation argument, which supposes that there's a very good chance that we are not actually real-life humans, that instead we are simulated humans, living in a simulated universe.
So Nick Bostrom refined this into a proper logical argument and showed that you need to kind of accept that either we are going to go extinct really soon, or we are, for some reason, our post-human descendants will never ever run simulations, maybe because they're impossible, or because they're very, very moral or have some coordination, or we are almost certainly in a simulation.
If you didn't recognize that voice, that was Anders Sandberg, Bostrom's colleague at the Future of Humanity Institute. Being an argument, the simulation argument doesn't provide evidence one way or the other, which is beautiful, because that leaves it to each person to be persuaded by it or not. But to get into it, we first have to agree on a couple of points. Remember when humanity's cosmic endowment came up all the way back in episode 3? That's the idea that if we are the only intelligent life in the universe, as it seems we are, then once we spread off of Earth, all the matter and energy that we can get our hands on before it expands out of our reach forever is ours to put to use for whatever amazing things we can come up with. If we manage to successfully navigate the existential risks that are coming our way and pass through the Great Filter, then it seems likely that our descendants, humans in the future, will use some of that cosmic endowment to create massive computers. Perhaps we will use nanobots to deconstruct planets to use as raw materials for those massive computers, and we'll build Dyson spheres to capture energy at the source of a star to power them. That our descendants will have massive computers seems like a fairly tame prediction as far as predictions about the future go. Think about how important computing is to our civilization today. It's a pretty good bet that as we continue moving along our technological path, computing will grow ever more important. And should we end up a post-biological society, computers will become even more important. They will provide the support structure for our very being. So if we're agreed that if we manage to save the world, our descendants will go on to have vast amounts of computation available to them, we can move on to the next point. That they will use some of that computing power to run simulations of us, their ancestors. They could have any reason to run simulations of human history. For fun, like the reason we play The Sims or Age of Empires, as a sociological or anthropological model, or as part of an educational exhibit that celebrates the time that we saved the future of the entire human race and intelligent life in the universe from near extinction. Whatever their reason, we can imagine that in the future, they might run what Bostrom calls ancestor simulations. Importantly, one of the beautiful things that makes the simulation argument persuasive is that it doesn't matter when this will happen. The argument puts no time constraints on any of this. Our descendants can build those computers and run those simulations 1,000 years from now or 1,000,000. It doesn't matter. Just so long as we can agree that at some point they will. So if we're agreed that our descendants will at some point in the future build massive computers and use some of that ridiculous amount of computing power available to them to run simulations of human history, we can now enter the simulation argument. It goes something like this. Either we are living in a computer simulation run by our descendants in the future, or we're not. If we're not living in a simulation, then that means we are what we tend to think we are, members of the real-life human race, living in basement or real reality in the 21st century, about 3.5 billion years on from the origin of life on Earth. But as plainly obvious as that may seem, the simulation argument raises a question. Why aren't we simulated? Bostrom identified a couple of possible reasons. One is that our descendants are fully capable of simulating us, they just choose not to. It's possible that our ancestors won't run simulations because their computing power is far too precious for even a minute fraction of it to be allocated to something potentially frivolous like an ancestor simulation. Or maybe the humans of the future are too moral to run an ancestor simulation. That the possibility that suffering could arise in the universe they create, like what we experience in our own universe now, is just too much of a moral gamble for their taste. In other words, they don't want the karmic mark against them for creating another universe where suffering lives. Or perhaps running ancestor simulations is just too hard. And of course, it's always possible they just don't feel like it. But take a closer look at this possibility. It shares the same fatal flaw with arguments that look to solve the Fermi paradox. It presumes that not one single future human decided to build a simulation of historic humans. Not a single person figured out a way to allocate some of that vast amount of computing power to simulate the universe and humanity in it. Not a single person came across a scientific study that would benefit from a model of human history. Not a single person was curious enough. Of the quadrillions or possibly sextillions of humans left to come, who will populate a span of time lasting billions of years, not a single one of them created an ancestor simulation. That's how it must be, because all it takes is one. For one person in the future to run one single ancestor simulation, and the simulation argument is activated. But there's another possibility as well. Perhaps no ancestor simulations are run in the future because there are no humans around to run them. Here's where the simulation argument ties into existential risks. If we're not simulated humans, in a very strange way, the simulation argument gives us a glimpse across the long expanse of time into our future. When we look ahead, it shows us that there are no humans around to run simulations of us. There are no humans who managed to spread from Earth and into the universe to put that cosmic endowment to use. It tells us that we will fail, that in the future, we didn't make it through the Great Filter. But if you think we will make it through the Great Filter, and if you're not convinced that not a single one of our descendants will run a simulation of humanity, you're in luck. There's a third option, that we are simulated humans living in a simulated universe. Yes, anybody can simply say that we are living in a simulation, just like anyone can say that we are living in what we call real reality. Neither one means anything. They're both just assertions. But the idea that we're living in a simulated reality actually has a leg up over the idea that we're living in real reality, thanks to probability.
Lovable, unpredictable, programmable. It's The Sims.
Back at the beginning of the year 2000, the software company Maxis released The Sims, a life simulation game where you, the player, controls individual simulated people. The Sims, as one reviewer put it, is a celebration of the mundane. Sims go about their lives. They go to work, they clean their toilets, and yes, they die. The Sims became an enormously popular game. Between 2000 and 2010, 125 million copies of The Sims and its successive editions were sold around the world. Each time one of those people brought their CD-ROM home, loaded it into the tray and booted up the software, a new iteration of the Sims universe was created. It was the same universe. It followed the same rules, the same program. It followed the same physics and logic, and the Sims all navigated their universe made up of the same set of possibilities. But each iteration was distinct and different. Each one was a discrete version of the Sims universe. And we can expect something along the same lines with any simulations our ancestors might run. Whether it's a scientific model for an anthropological study of history, or whether it's the software of a popular game, whether it's a class project, each time that simulation is run, a new iteration of our simulated human universe is created. Say that at some point in the future, again, it doesn't matter when, but at some point across the billions of years, among the quadrillions of people left to come, there's a 10-year period where an ancestor simulation software that is equally as popular as The Sims is created and sold. As all those future humans load their simulations, a new iteration of our simulated universe is born. Each following the same guidelines, the same code, each taking radically different courses within the same set of prescribed rules, the same set of physics, as it were. If we're agreed that our descendants will run ancestor simulations of us, and that we don't have any frame of reference to distinguish the simulation from real reality, and in the future, 125 million iterations of that simulated universe are run, then you and I, and everyone alive in our universe, has a 1 in 125 million chance that we are actual humans. A 1 in 125 million chance that we are not simulated. Or to put it somewhat less encouragingly, there is a 99.9999992% chance that we are simulated humans living in an ancestor simulation being run in the future. Because there was one iteration of humans in real life, there is a chance that we are members of that genuine human race as we like to think of ourselves. But, well, here's Nick Bostrom.
It's a little bit as if we as a species thought we were Napoleon. So there are a lot of people who have thought that we're Napoleon. There has only been one actual Napoleon. There have been many more people who thought that we're Napoleon than who actually were Napoleon. So if you think you're a kind of an emperor of world historic importance, chances are maybe you're actually a lunatic in an insane asylum.
Because so many simulations are run in the future, given that we have no frame of reference to tell us any differences between our reality and basement reality, that utter lack of signs that we live in a dream, as Descartes suggested, the chances are vastly greater that we are simulated rather than real. There's just simply been more simulated humans than real ones. And being members of one group or the other, the chances state quite plainly that it's likelier we're members of the simulated group. You can mess with the numbers either way to make the chances go up or down. Say that ancestor simulation is way more popular than The Sims ever was, and an equal amount of copies are sold each decade for 100 years. That would mean that we had one chance in over 1 billion of being a human, and so on. Each new iteration of our simulated universe lowers the chances that we are real. But, like I said before, even just one ancestor simulation run in the future activates the simulation argument. Even if just once in the whole future history of the human race, only one iteration of our simulated universe is run, we still have even odds that we're simulated. If we make it through the Great Filter and our descendants run ancestor simulations of us, we have at best a 50% chance of being real humans. I should say that if it does turn out that we are simulated, our simulation could have been built by any number of things. It's possible the people who created us aren't future humans at all, but some other intelligent life entirely. It could be a race of Martian ancestors that real humans diverged from eons ago. An intelligent machine, super intelligent mice looking for the answer to the meaning of life. It's even possible that our universe follows a more basic set of physics than what governs the universe our universe is simulated within. Perhaps there never was a one true race of real-life humans, any more than there was a real-life race of Sims. But the thing about the simulation argument is that it calls for the least amount of speculation, the least amount of unreality for it to be right. All it requires is that our descendants will run simulations of humanity in the future. It's rather elegant in its simplicity. That's what makes it convincing. Even still, there are, as you may imagine, a number of objections to the simulation argument. Some people simply detest it on its face, dismissing it out of hand as nothing more than material for late-night conversations in college dorms. But others engage with it seriously, and they raise legitimate issues. The thing is, it seems that every objection leveled against the simulation argument either imposes unnecessary time constraints or is just a simple failure of imagination. If this is the first you've heard of the simulation argument, at this point you might be looking around you, closely examining the edges of things, seeing if you can tell that the world is fake. Don't bother. The simulation argument doesn't change a single thing about our universe. The physics are the same as ever. Being persuaded that we live in a simulation doesn't unlock some greater understanding of our reality such that we can alter it in ways that we couldn't before. There's no pill to choose. There won't be any flying around or walking through walls. Nor should your morality be altered. Your mother is just as real as she was before, and she would be just as disappointed as before if you decided to start a life of crime because we're simulated, so why does it matter? The court system is real too, and you would be imprisoned by it just as sure as ever. And when you explain to them that none of this is real, that they aren't real, the car you set fire to isn't real, that the whole universe isn't real, the mental health system will be just as happy as ever to lock you away in a padded room indefinitely, the walls of which you would find you were fully unable to will yourself to walk through using your newfound awareness of the simulated basis of our universe. Our universe is as real as it ever was. The only thing the simulation argument can change is your perspective. One common objection to the simulation argument kind of falls under this umbrella of misunderstanding. It goes something like this. How could a simulated banana, or a simulated apple, or a simulated cheeseburger possibly provide nutrients to us? How could it sustain and nourish us, alleviate our hunger, make us feel full? It's kind of like the hard problem of consciousness, the puzzle of how we get from neurons firing to subjective experience. Sure, you can simulate a banana, but you're simulating a banana. It's on a computer. And those of us who are looking at the banana know we are looking at a banana pictured on a computer. How can we account for the experience of interacting with a banana, holding one, peeling it and eating it, of being allergic to it? How would we get from a simulated banana to the experience of a banana that is indistinguishable from reality? The answer is rather simple. We're not simulating that banana or cheeseburger or whatever, so it's not a simulation to us. It's made of the same stuff that we are. It's no more fake than you. You're no more real than it. We share the same reality. The banana isn't a simulated banana in our universe. It's just a banana. So it's subject to the same rules that we are. On the quantum level, those bananas are made up of energetic vibrations, just like us. They form particles that are held together by the fundamental forces, just like us. And they form larger and more stable structures that increase in size and complexity up to the level of what we think of as a banana. And when we eat that particular package of energetic vibrations, it interacts with our own energetic vibrations in such a way that we experience taste and the sensation of deliciousness. We experience feeling full if we eat too many of them, and our bodies break them down into smaller parts, and we use those parts for energy, same as ever. Banana objections, as we'll call them, are rooted in the idea that we exist in some different reality from the banana. To be clear, the simulation argument does not suppose that there's some real version of you elsewhere. What we experience as our universe, bananas and all, is a simulation to someone else. To us, it is our full reality. So to answer the banana objection, the banana can satiate and sustain us because it's as real as we are. Other objections go a little deeper. How could we possibly simulate the universe on anything approaching a detail fine-grained enough to be indistinguishable from the original? And there are a couple of answers to this one. First, we can't. We don't have the computing power to faithfully render the universe in that detail. But in this objection, we run into an unnecessary time constraint. While we can't faithfully reproduce the universe, there's a pretty good chance that our descendants will be able to. We, those of us alive today, are already on track to doing this. For the last several years, humans have been able to produce accurate simulations of quarks and gluons, and the strong nuclear force that binds them together. These models are not infinitely precise, but they're faithful enough to reality that a simulated scientist living in the simulated universe where the protons exist would have no way to distinguish their unreality. They would just be protons that behave and appear exactly like any other protons. The models that we can produce today simulate an exceedingly tiny portion of our universe. They're on the scale of femtometers, about a quadrillionth of a meter. But the models show a proof of concept that simulating the universe is possible. And they also show that the human race already has a desire to simulate the universe. Already at this early stage in modeling the universe, we found that there are problems future humans will run into when it comes to scaling up those models. It's pretty obvious that modeling the entire universe would be a very, very difficult undertaking. But difficulties can be worked out over time. The problem comes when we reach impossibilities. And in 2017, a pair of researchers from Oxford University found an impossibility that seems to show pretty conclusively that we do not live in a simulated universe. The researchers found that it would be physically impossible to simulate at least one aspect of the universe, something called the quantum Hall effect, which describes the way that electrons bounce between energy states, called a quantum leap, in the presence of a magnetic field and extremely low temperatures. It occupies as arcane a corner of particle physics as there is. But the point is, the researchers found that to accurately simulate the effect, the computational power required doubles each time you add a new particle to the model. Rather than increasing the power needed by 1 unit, it grows exponentially. So within just a few hundred particles, the operations per second required by a computer to run a simulation of the quantum Hall effect grows to a total beyond the number of atoms there are in the universe, around 10 to the 82nd power. Not only is that number vastly more operations than our computers can perform today, this also presents a major technical issue. We need electrons to perform the computations that create the simulated model in the first place. Electrons are what we use to carry information in our computers. And as we simulate more and more particles subject to the quantum Hall effect, we will start to require a substantial portion of the electrons that are part of those 10 to the 82nd power atoms in the universe. And as you may know, those electrons are otherwise occupied, performing other functions like making up all the matter in the universe. Which means that eventually it becomes physically impossible to simulate the quantum Hall effect. And since we can observe the quantum Hall effect in our own universe, we can reason that our universe is not a simulation. But this presents a failure of imagination, not an impossibility. Indeed, the researchers who made the discovery noted that their finding only showed that we couldn't possibly be simulated within a traditional computer, the type that we have available to us now, the kind that uses electrons. They also pointed out that we can probably safely presume that the humans of the future would be simulating us on better computers than what we're using today. I've said it before, and I'll say it again. If it turns out that the humans of the future don't have better computers than we have now, it would be one of the more surprising things in this entire series. And indeed, we are working on better computers already, specifically quantum computers, the type of computer that processes information not gleaned from the movement of electrons, but instead from the interaction of elementary particles, which exponentially opens up a computer's capacity to perform calculations in a single second, and neatly transfers rendering the quantum Hall effect in a simulation from the impossible column over to the column marked possible. We've already talked about that to accurately simulate a human would require simulating a mind that is capable of subjective experience. If the hard problem of consciousness isn't actually a problem after all, then by creating an accurate model of all of the bits that make up a human mind, the neurons and synapses, the neurochemicals, we can imagine that they will produce subjective experience when they interact with the matter and energy that makes up the simulated universe. This is exactly the same concept as a post-biological civilization that has shed their physical form and migrated onto computers. If you found the concept of a post-biological future for humanity plausible, then you should have no trouble accepting the simulation argument. The only difference between the two is that rather than us migrating onto computers ourselves, we will have always been there already. As Nick Bostrom points out in his paper on the simulation argument, the human brain can process about 10 to the 17th power operations per second. If that's the amount of processing power it takes to experience subjective reality, then that's about what we would expect it would take to simulate a human mind. And to run a simulation of all of human history would require that amount times around 107 billion, since that's the number of humans who've been born up to this point. Although we can imagine that as humans die, the processing power required to produce their subjective experience would be freed up to power the minds of new humans as they're born. So perhaps all you'd ever need is enough processing power to simulate all of the minds of the humans who are alive at any given point. Which means that to simulate a global population of 10 billion people, you'd need a computer capable of processing 10 to the 27th power operations per second. That's not including the processing power it would take to simulate the universe, which we could expect would expand the requirements to mind-boggling numbers. There are surely a lot of corners future humans can cut to create a simulation. They wouldn't need to simulate the entire universe, obviously, just what we can detect. Then it's possible they wouldn't need to simulate the universe at all. Rather, they could just create a program that stimulates our minds directly to experience the universe. Even with these shortcuts, though, there's still an enormous amount of ground to cover before we get to the point where we have the processing power of the magnitude required to simulate a human mind, let alone all 7.5 billion of us. Take this for example. Back in 2014, the Fujitsu Corporation ran a test on its Fujitsu K, at the time the fourth fastest supercomputer in the world, a ranking that is no small feat. In the test, the Fujitsu engineers wanted to see how long it took their K computer to process 1% of the amount of information that a human brain can process in 1 second. The K managed to process that information, but rather than the 100th of a second it would have taken a brain, it took the computer 40 minutes to complete the task. And it's worth noting, the K required 12.7 megawatts of electricity throughout the 40 minutes it was running this test, about the same amount of electricity needed to power the entire city of Sacramento, California. Considering the gap between where we are now and what's required to run a respectable ancestor simulation, it might start to seem that such simulations are indeed impossible. But easy there. We're only running up against an unnecessary time constraint again. Given enough time, it seems quite possible to build a computer that could run an accurate simulation. As Bostrom points out, a single one of those planet-sized computers could perform 10 to the 42nd operations per second. To run an ancestor simulation would require just the slightest fraction of that computer's processing power. And we can imagine that in a far enough expanse into the future, if our descendants have one planet-sized computer, they will eventually have a great many of them. And let's not forget, we humans have a long-standing tradition of advancing by leaps and bounds in computing. If you wanted to find the top of the line in supercomputers back in 1985, you needed to look no further than the Cray 2.
Recently, scientists producing these simulations at NASA's Ames Research Center in Mountain View, California, began using a new supercomputer, the Cray 2.
It was just a little smaller than the size of a VW Beetle stood on its end, but the Cray 2 could perform 250 million operations per second, an astounding amount in 1985. Just over 30 years later, Apple released a computer that could perform 600 billion operations per second. Apple called theirs the iPhone X, which, by the way, is run by a machine learning algorithm capable of self-improvement. We already share the planet with quantum computers, the very kind of computer that could simulate a universe to a detail down to the quantum grain. The ones we share the planet with today are exceedingly slow compared to our current traditional computers, but they are in the earliest stages of development. It was only in the 80s that physicists began designing quantum computers that could work in theory, and only in the 90s when the first quantum computers were built. We can imagine that if we continue to follow this arc, those primitive quantum computers of today will advance as well as our traditional ones have. We haven't even lived with traditional computers for a century yet. Imagine what our quantum computers will be capable of a century from now. There are, to be sure, numerous other objections to the simulation argument, but most, if not all, have difficulty overcoming that non-limitation of time. When we give our descendants the luxury of time, those people whose future lives we will save by taking on our existential risks become capable of anything that we can imagine and more, including simulating us. Back in 2012, a group of physicists from Bonn University in Germany announced that they had figured out a way to test whether we live in a simulation. If our simulation is anything like the femtometer scale simulated models of protons that we can produce now, then that means it isn't an infinitely accurate copy of the real universe predicted by Einstein's theory of relativity. One of the things that relativity says is that the universe is built from a structure made up of the three spatial dimensions and time, space-time. Space-time is the fabric of our universe, and it's contiguous. One giant universe-sized unit. There's no gaps in it anywhere, no matter how far we zoom in. Remember when energy fields came up in the physics episode, and I mentioned that these energy fields are everywhere, at every point in time and space? That's what that means. There's no place where those fields aren't, because there's no gaps in space-time. There's no place where space doesn't exist, just as there aren't any gaps in time where there's no time. It would take an enormous computer to render an infinitely accurate version of our universe, potentially one the exact size of the universe. And so we might guess that the designers of our simulation would be forced to make a version that's just slightly less accurate than the real thing, which would mean that the fabric of the simulated universe wouldn't be infinitely smooth. There would be gaps in its structure, gaps between the individual units that it's built from. If we could only zoom in close enough to examine it, we would find the fabric of our simulated universe was pixelated. But we can't zoom in that close to observe space-time directly, so the Bonn University researchers suggested a way that we could indirectly observe it, by watching how the smallest bits of matter in the universe, ultra-high energy cosmic rays, travel around space. Remember, cosmic rays are high-energy particles, most likely spit out from supernova, that zip around our universe and collide with other particles, and may or may not produce microscopic black holes when they do. They're one of the things that we model in particle colliders. If space-time is contiguous in our universe, as we think it's supposed to be, then cosmic rays should travel in every possible direction. Since there's no gaps in space-time, there's nothing to direct their paths. There aren't any channels in the fabric of space for them to fall into and travel along. But if space-time is pixelated, the very fabric of the universe would form an infinitesimally fine grid. There would be tracks that the tiniest cosmic rays might travel along. So, say the Bonn researchers, if we manage to observe that cosmic rays follow a grid pattern, or that they show a preference for traveling at angles rather than moving in every possible direction as they should, we might have a fairly good indication that what we're viewing as reality is actually a simulated version of it. Interestingly, the idea that space-time is grainy rather than smooth is starting to gain traction among physicists. The absolutely smallest discrete measure of distance in the universe is called the Planck length. Anything smaller than it, and physics just falls to pieces. It's difficult to get across how small a Planck length is. It's about 100 quintillion times smaller than a proton, which itself is about 100,000 times smaller than an atom. In fact, if we could zoom into the Planck scale so that a Planck length was the size of an atom, the atoms in the universe would be the size of galaxies. It's that small. Since space-time is supposed to be infinitely smooth, it's weird that there's a smallest point beyond which physics is just meaningless. It's possible that our math is wrong, or that when we manage to marry relativity and the Standard Model into a theory of quantum gravity, we'll find that physics picks up again beyond the Planck scale. But some quantum physicists are beginning to wonder if perhaps there is some non-infinite bottom size to the fabric of space-time, and that the Planck length may be it. Perhaps we're beginning to uncover the frame of reference Descartes longed for to distinguish between our reality and real reality. But even as we chip away at the nature of our own reality, if we find that we are indeed simulated, we run into an issue. We still don't know anything about the nature of real reality. All of our questions just get kicked up to the universe that's simulating us. There's a problem with that, because we can't say for sure that the universe we are simulated within isn't simulated itself. So the problem can be kicked up indefinitely. Since in the simulation argument, the people who are simulating us are also humans themselves, they are, remember, the descendants of the people we're simulations of. The same staggering probabilities against us being real-life humans applies to them as well. Just by their membership in the human race and the existence of ancestor simulations, the people who simulated us have that same 99.9999992% chance of being simulated. Just because they are running the simulation of their ancestors doesn't identify them as members of the real human race. A simulation can run inside a simulation. When our descendants run ancestor simulations in the future, there will be simulated versions of the universe existing within our own. But if we're simulated, then the simulations we run will be simulations within our simulation. And the same possibility applies to the people running our simulation too. Their universe may be simulated as well. Perhaps it's an almost certainty that once a simulated group of humans reaches some specific point, they will begin to run ancestor simulations themselves. The ones that make it through the Great Filter, at least. And so ancestor simulations spread in each direction from our own universe. Simulations within simulations within simulations. Kind of like how it looks inside an elevator that has mirrors on all sides. We enter what's called an infinite regress problem. We can figure out that our universe is simulated, but what does that tell us about the universe the people who are simulating us live in? Actually, this is familiar territory for physics. One implication of cosmology is that our universe is one bubble amid an infinite froth of bubbles, each their own universe. And since our universe is an isolated system, no matter or energy can leak out of it, and we presume the same about those other universes. Which means that we can't glean any information about those other universes that we rub up against in the infinite froth, and we likely never will. And yet, you would be hard-pressed to find a physicist who suggested throwing in the towel on investigating our own universe when cosmology reached this conclusion. The same holds true for the idea that we're simulated. Not being able to know anything about the universe that simulated us doesn't mean there's nothing to be gained from investigating our own. It's worth taking a step back here to look at the implications of what it means when we start talking about who is simulating us. We're talking about someone who, in some respect, created us. Perhaps one of the touchiest aspects of the simulation argument is that it suggests a sort of techno-creationism. Although it does fall under the umbrella of creationism, accepting the idea that we may be simulated doesn't require any form of supernatural or religious belief. If we're simulated, we can identify who created us. It's the descendants of the people who we're simulations of. Future humans created us. But who exactly? Would the software developer who wrote the code that produced us qualify as our creator? Would the person who directly booted up the simulation we live in? Or what if our simulation is a scientific model? Does our creator wear a lab coat and our simulation is a digital petri dish of sorts? Or is our creator a far future teenager who created us for a class project? I should remind you that it's important to remember the simulation argument doesn't prove anything about our perceived reality. It gives no evidence one way or the other. It's a framework for viewing the nature of our universe, which means that, like any other argument, you can take or leave it. It is a matter of personal belief whether the idea of being created from a program written by future humans is more or less comforting than the idea that a supernatural deity created us, or that the world grew on the back of a turtle, or that we're the fluke result of an incomprehensible series of cause and effect stretching back nearly 14 billion years. If we did one day discover that we are simulated humans living in a simulated universe, that would, we can imagine, have enormous and sweeping effects on us. Even if you already believe that we were created, how would you feel to learn that your creator is only human, with all the same faults and flaws that you have? And if you don't believe today that we were created, that we are merely the result of some physical processes that can turn dead matter into cellular life, and that we were shaped by the forces of evolution, learning indisputably that we were indeed created would be a tough pill to swallow. But would those enormous and sweeping effects be all bad? And would they be permanent? This is Anders Sandberg again.
I do think that if we realize that the universe fundamentally worked differently from how we used to believe it was, we would be shaken. But we would also get over it, just like we have gotten over heliocentrism and evolution and Freud and so on. Most people are way more resilient to upsets of the fundamental structure of the world than we give them credit for.
We humans are really good at absorbing terrible news, whether it's a cancer diagnosis or learning that we're facing existential risks. There's a chance we will survive, there's a chance we won't. But do we simply lay down and die? Humans tend not to do that. Instead, we carry on. We seek out connections and support from other humans who are also carrying on. And we might expect the same would hold true should we learn that we're simulated. Even despite finding that we are the result of code, nothing about the meaning of our lives should necessarily be lost.
Well, where do we get a meaning in our own lives? And I would argue that we're actually creating it ourselves. Even if the universe was a class project to demonstrate a sociological thing, that doesn't mean it's the meaning of our life to now behave socially. It's not like our loves and emotions become meaningless. We might still have a meaning that's very different from the reason the simulation exists.
It will probably be tough to keep in mind, especially for the people who are alive at the time when we learn our universe is simulated. But at bottom, really, nothing much changes for us. Our understanding of our nature only deepens. In a very direct way, learning we are simulated would focus our investigation into our universe. It would certainly explain a lot. The Bonn University researchers who came up with the cosmic ray grid test suggested that perhaps we'd find the reason the Higgs field isn't in its lowest energy state is because of a rounding error in the computations that produce our simulation. Maybe the measurement problem, that quantum particles seem to exist in all of the possible forms they can take at the same time, is a shortcut to make rendering the universe more efficient. The fine-tuning we see would certainly be explained. The parameters of the forces and energy that make up our universe would have to be the way they are, because we could not be produced under other conditions. But that's correct whether we're simulated or not. Finding we're simulated would identify computer code as the basis of those governing principles that we already take to be true, like abiogenesis and evolution. We wouldn't expect that understanding the truth of that would change how those processes function. But perhaps we could learn how to change them ourselves. Maybe learning we are simulated would free us to abandon the notion of fate and take control of how the universe operates to shape it more to our liking. After all, isn't that what the study of physics is? Taking control of the universe would also focus the moral responsibility that we have in making our universe a better place. Having the ability to reduce suffering wherever we found it, we would be morally obligated to do so. But then, that's the case already as well. The difference is that we couldn't let ourselves off the hook by chalking that suffering up to inevitability like we do now. This is Seth Shostak, the senior astronomer at SETI, who you met in the first episode on the Fermi paradox.
The question that I asked Professor Bostrom that I think was most relevant to me was, okay, if this is all a simulation, if this conversation we're having is not real, it's just code, right? If it's all just code, do I have to live a moral existence or can I just have fun? He thought it was better to live a moral existence. And I thought that was kind of a testimony to how he really felt on the matter, that, you better act like it's real.
The beautiful thing about the simulation argument is that it doesn't change anything, only our perspective. The world continues to operate in exactly the same way as before. It's just that some of the mystery is brushed away. Nothing about humanity changes, nor does anything about where we find ourselves. In the position where, as Toby Ord paraphrased Carl Sagan, we humans have grown powerful before we've grown wise. The existential risks we face remain as real as ever. And if we did find we are simulated, our existential risks would only sharpen, since we would learn of a new one, that our simulation could be turned off, which I suppose would qualify as a natural existential risk. Whether we arrived at this point where we have grown powerful before we've grown wise by total fluke or by predetermination, whether we are members of the real human race or simulated, we are in the same unique and precarious position that we were in before. We are still entering the mouth of the great filter, and we are still at risk of our existence coming to a permanent end. If we fail to come together as a world and learn to use science to help us grow wiser faster, we will surely not survive. We will accidentally wipe ourselves out with our unwise power, and that will be the end of humans in our universe. Does it matter whether that universe arose from a Big Bang or from a system boot? Whether we are real or simulated, our reality is the same.